Now, this is the type of questions which may come, as you were asking how the questions may come. So we have seen already complete designing, and one of the major application of the decoder is that, girls, that by using decoders we can design any function. Yani, you have seen already previously, if we have given f is equal to, for example, any sum of minterms 0, 1, 2, 3, 4, something like that. Minterms are given. So we can design this one by using decoder. We don't need to use AND gate, OR gate, something like that. We can make use of this decoder to design that one. Similarly, so in this question, what we are going to do, we are going to design a full adder using a decoder. So if you want to use decoder to design any to implement any function, that function must be represented in the minterm. And we should know the minterm. If we know the minterm, we can use it. So for the half adder and full adder, these are the expressions. How these expressions are coming, you go back first to see the half adder and full adder, because it was covered last week. So maybe you have skipped this point. So just go back for the full adder. This is the full adder design, girls, right? Yes. Here is the full adder. So here the table you can see, and you can see here the two outputs C and S. And S is what are the minterms. You will see the minterms are 1, 2, 4, 7. See the minterms of carry, which
3, 5, 6, 7.
6, 7. Now, so now you know the minterm. So if you know, as I said, minterm of any function, you can design by using decoder. It's so simple, very easy. So one of the design by using basic gate, we have seen this way. We can design full adder here. This is the design of full adder. We have seen another design. This is a design of full adder by using basic gate. We have seen one more design by using 2 half adder, like that. But we can also design it by using decoder. So we'll see now how can we do it, how a decoder can be used to implement any function. So here is the question which may come like that: design a full adder or design a full adder using 3 to 8 line decoder. Now, how do we know if the first type of question come, whether we should use 3 to 8 line or 2 to something? So when you see the full adder, girls, you know that how many inputs are there for the full adder?
3.
3. So we need to use 3 to 8 line decoder. It's very simple. Now, right, it's first the minterms. Girls, if you remember, I told you for the decoder, the outputs are representing the minterms. Do you remember? Outputs of a decoder basically represent the minterms. So y0, what it will be representing? Will it be representing? Will it be representing?
All zeros, and the last one will be 1.
So it is like it will be representing x complement, y complement, z complement. Yani which is m0, minterm 0. This is minterm 1, minterm 2, minterm 3, minterm 4, minterm 5, minterm 6, minterm 7. Are you getting my point?
Yes.
Okay. Now look for this expression S. What these minterms are communicating here? They are saying the output S will be 1, will equal to 1 if the input is 1, either 2, either 3, 4 and 7. So if any input is there, S will be high. Are you agree with this point?
Yes.
You have seen the truth table. In that truth table, the S value is 4 times high. It means is that if the input is 1 or 2 or 4 or 7, yani which logic is there? Or output S will be 1. Similarly, for the C value in the truth table will be high if the input value is 3 or 5 or 6 or 7. Do you get my point?
Yes.
Yes.
Okay. So in order to design this one, it's so simple. Just use the OR gate at the output of the decoder and connect these minterm with that OR gate. See now. We just use two OR gates because full adder have two outputs, which is S and C, and we connect the minterms with that one. So S minterms are 1, 2, 4, 7. So 7 is connected, 4 is connected, 2 is connected, 1 is connected there. So if any of that output is high, S will be high. Similarly for the C, this is 3, this is 5, this is 6, this is 7. Clear? Are you getting the point? Are you getting the point? And do you know how the full adder works? 3
Yes.
bits will be added, like X plus Y plus Z. Then what it generate? Sum and carry. Let's just consider some value 0, 1, 1, 0, 1. When you add it, what you will be getting? 0. And what is the output?
And 1 carry.
Yani this is carry and this is sum. Okay. Now check. Is this working same way? This design. When I put here 1, 0, 1. So how the decoder works? Only one output will be high. Can you tell me which output will be high now?
Okay.
Which output will be high now of this decoder? Girls, I just explained the decoder functioning. If the input is 1, 0, 1, which output will be high? All output will be high of the decoder, or one particular will be high?
Only carry. One
Why
carry.
are you going to the carry? I'm asking the output of the decoder. Carry is the output of the decoder, or carry is the output of the AND gate? I'm asking the output of the decoder. These are the outputs of the decoder.
Y5.
I5, yes. So because of the input is 5, 1, 0, 1. So at that time, Y5 will be high. This will be the 1. Rest is gonna be 0. So can you check where you are connecting this one? Are you connecting the one with the S? Yani this gate? Gate number 1? No. So it means others inputs are 0. This is 0. This is 0. This is 0. So what will be the output here? This will be 0. What about the next gate, which is gate number 2? You can see, because you are connecting this Y5 with that one, it means one input is 1. Others are 0. So what will be the output of this OR gate? This will be 1. So this is basically working the same way as a adder. Clear now? Understand?
It should be one output, one high. لل
Yes.
decoder. For example, 7.
So
it could be.
Decode. See here, I explain you very well how the decoder works. Do you have any confusion how the decoder works?
Doctor, I had confusion in this one. How did 5 is 1?
What is this? How decoder works? Go back. It means you did not understand anything. You go back, more back, and then you look here how the decoder is working. First of all, better you go very first, here. This is decoder simple. What I did here. So don't you know this truth table? What this truth table is saying? According to the input, a particular output is gonna be high. Check. Yeah, all the outputs are high. This is the functioning of the decoder, the basics of the decoder, how it works. According to the input value. So if the input value is 1, 1, which is 3. So one output is gonna be high, rest are gonna be zero. So same thing is there. What I'm changing here, new thing. If you have this decoder, your input is, for example, 111, 3 inputs 111. So only one output will be high, which is Y7. Rest are gonna be zero.
Okay.
This is very basic. The same thing I explained 2-3 times. Then I am using there. If the input is 0, 0, 0, for example, so yani Y0 is gonna be high. Rest are gonna be zero. So what is the any problem here to understand? This is very basic thing. What I am asking there. So now same thing I am telling you there how it is working basically. I did not add anything new there which you are not getting, which is confusing. What is here in this one, in this example? You are going to design this one, and I told you what does it mean? It means is that S and C. So can't you see this one? If you go back for the full header, even I show you the full header. I don't know, maybe you are not focusing, that's why you skip this point. I just explained the thing. Can't you see this truth table of the full header? And I told you the S value is 1 if the input is 1. Another one is here, another one is here, another one is here. What are the values? This one 0, 0, 1. This is minterm 1. This is minterm 2. This is minterm 4. This is minterm 5. So any one of them present, the output will be 1. This is what I said. Similarly for the C, the output, yani these are the minterms, 4 minterms. So if input is 3, if the input is 5, if the input is 6, if the input is 7, any one of them is present, the C will be high at that time. This is what I just said. So what this minterms are telling you there, we are now designing this one accordingly.
Yes, clear. Thank you.
Now, this is what I said, because there are 2 outputs of the full adder. So I need to use 2 OR gates. OR gates, why? Because if the input is 1, if the input is 2, 4 or 7, or any one of them present, output will be high. So we connected here 2 OR gates. We connected this way, these minterms we connected for the S, Y7, Y6, Y5 is there for the C, it is there, 3, 5, 6, 7, we are connecting. And now if I give you example, how the adder works. If you are adding 1, 0, 1, what should be the result? So I told you this is 0, 1. Now you look how it is working. When you give here input 1, 0, 1, as per the working of the decoder, Y5 will be high. Rest are gonna be 0. And where Y5 is connected, because Y5 is not connected with the S, this will be 0. But it is connected here with the C, this will be 1. Because if any input of the OR gate is high, output will be high. This is what I explained. It is very basic thing, any basic understanding of adder, the decoder. Similarly, if you have any other function, you can also design by using decoder, provided you should know the minterm. And you don't need more decoders to design if you want to design 2 functions by using a decoder, 1 decoder is sufficient. If you want to add more inputs, no problem, you can use 1 decoder. But what you need to increase the OR gates. Here you can connect more and you can connect it. So that the thing is, number of expression is equivalent to the number of OR gate. 1 decoder is enough, because as I said, the decoder generate the minterms. So 3 inputs, 8 minterms are generated, which is, you will check here according to the function which minterms are present, just connect accordingly, and this is the way. So this is the one design by using OR gates. Same thing can also be designed in a different style, which is, this is the implementation, which is the what? Not NAND gate, inverted not NAND gate. Here is also working the same way. If you want to check it, it is working exactly same way. Yani if you add 0, 1, 0, answer will be 0, 1. Check it. When you say again 0, 1, 0, so 5 is gonna be high and rest are gonna be 0 as per the working of the decoder. You check now, because this is connected here. So because of this inversion, this value will be here 0, rest are gonna be 1 because of they are inverting. So if any input in this AND gate, because it's what is the operation? Invert and then invert. So this is the ending operation. So 0 will multiply by 1, 1, 1. So output will be 0. And then there is a bubble inversion. So what will be the value of C now?
1.
1. What about the S? For the S, are you connecting I5 with the S? Y5 with the S?
No.
No. So others are already 0. We know that. So 0 will be inverted here. It means all will become 1.1.1 because AND operation. This is AND operation. So all are 1, 1, 1, 1, 1. What is the final result? 1. 1. Then you have inversion here. What 1 will become? 0. So it means sum is 0, carry is 1. So this is the carry 1 and this is the sum. So this is another style of designing. By rather than using here OR gate, we are using inverted NAND gate. See one more design, which is active high decoder type, active low decoder. So in active low decoder, what you can remember here, that if you are implementing by using active high decoder, you will be using OR gates, previous example. But if you want to design by using active high, this is what, sorry, active low decoder. So which gates you will be using? NAND gates. NAND gates. Or in case of active high, OR gates, which we have seen the previous example. So it will be working in the same way. If the input is 1, 0, 1, particular output is gonna be 0. Particular output is going to be 0. Which particular? Yani this one 0.
5. The rest will be 1.
Rest will be 1. So you can see this is connected to C only. So C is having one input as a 0. So AND invert. So it means 0 is the final product of these inputs, then inversion. It will be 1. But by the way, this 0 is not connected to this S. All are now 1, 1, 1, 1. So final is 1 and after inversion, it become 0. So this way we can also understand the working. So designing is very simple. Just connect NAND gate if you are implementing by using active and connect the input to the NAND gate according to the given minterms of the function. If you want to implement 2 functions, you need 2 NAND gates. If you want to implement 5 functions, you need 5 NAND gates. If you only one, so only 1 NAND gate. This is the way. Clear? Any question now?
All clear.
Okay, so this is a decoder application. Now we can have a break if you want. So yes, this is the encoder, which actually performs the opposite of operation of the decoder. So if decoder is clear to you, encoder will also be clear to you. If there is a doubt there, you can ask. I think it is clear. So encoder is what basically, which consists of 2's power n input lines and n output lines. So it is a digital circuit that performs the inverse operation of the decoder, and encoder has 2's power n or fewer input lines and n output lines. The output lines as n aggregate generate the binary code. It generate the aggregate binary code corresponding to the input value. So for example, here yani at a time a particular input is gonna be high. Accordingly, the binary value of that input, it is gonna be generated at the output. For example, if I say this one is high, rest are low. The rule is that at a time, only one input is gonna be high. Okay, so because of this input is high, which is x2, so the output will be binary value, which is 2, 1, 0. Similarly, if this one is high, rest are 0, yani x0 is 1. What will be the output at that time?
0, 0.
0, 0. Exactly. This is the way basically how the encoder works. Okay. So this is basically performing the opposite operation or inverse operation of the decoder. This is the way. So here is a limitation that at a time only one switch, because we can connect here switches. I'll show you this one, the use of it. We can connect here switch and we can control control the appliances. We'll discuss this thing. So here we have only one at a time, one output will be high, either this or this or this or this. Accordingly, the value, binary value is going to be generated at the output, either 3, 2, 1 or 0, which you can see here. Again, this is without enable control. We can also have the enable control. If there is an enable control, which is as we have seen earlier, E, it means if E is 0, definitely it will be the, not this side, it will be this side, enable. So if E is 0, it means you keep on giving any input here, output will always be, 0. There will be no change in the output if you make it 1, 1, 1, something like that. Sorry, not 1, 1, 1. This is like 0, 0, 0. We want to make it 1, but no change will be there. So enable is also possible, just to let you know about the enable. And this is the use of it, like encoder, decoder. You have seen, you have heard that terminology, what we call encryption, decryption in terms of software. Okay, we need to perform encryption at the receiver side, and we perform the opposite at the decryption at the receiver side. So transmitter and receiver, it's like that. So transmitter side, what we perform? Encryption, and the receiver side, we perform decryption. Like here, we are transferring some information, like we want to control the buses by using these the bulbs which is here, by using these switches. So girls, if we want to connect 1 to 1, yani one bulb to one switch, we need how many wires? How many wires we need to connect one switch to one bulb?
1.
No, but how many bulbs are there?
For this example, only 3.
No, this one. How many bulbs are there? They are the bulbs at the output. 8. Right? So we want to we want to control it. So how many switches we need? We need 8 switches, 1-to-1 connection. But for example, we are not going to turn on or control all 8 bulbs, at same time. We need to just, perform either one control at a time. If this is a situation, so we can save the lines, number of lines, by only 3 lines. So what will happen now? As if I press switch number 1, which is high, rest are 0. We know that the rule is that at a time only one switch will be active, rest are gonna be 0. This is the rule to use it. If it is the case, so here is the one, yani this one. So what will be the output here which will be generated? It will be generated like 0,
0, 1.
0, 0, 1, exactly, 0, 0, 1. So 0, 0, 1 will reach at the input of the decoder. And do you know that when the input is 0, 0, 1 of the decoder, which particular output is gonna be high? 1.
1, yes.
1. So at that time, okay, actually they are up, this should be down, yani this is 0, this is 1, it is like that, okay, there is some misplace here. So this is the one. So this is going to be high. When it is high, only this bulb will grow, rest are off. So this is the use of it actually, you know, one of the application of the encoder and decoder that we have seen some. So they are used in, you know, together as a pair. We use here encoder at the transmitter side. We use decoder at the receiver side basically. So this is one of the example or application of the encoders. Other also girls, as we have seen, the inputs are 2's power n, 2's power n, and the outputs are n basically for the encoder. So for example, if we say n is equal to 3, it is yani, it is 8 to 3 line, you know, encoder. And 8 is what basically we call octal and 2 binary. So basically how it is working, we know that 8 out inputs and 3 outputs. So you see this one, octal, we have only digits 0 to 7. So we have here 0 to 7 inputs. So if this input is high, yani we are just looking what should be the binary equivalent of octal 7. So the output will be 111. We will be getting for the you know, encoder. So basically this encoder is converting octal number, okay, into the binary. So we just wanna, okay, check what is the, you know, 6 in octal 6 in binary. So we will just press 6 at a time and you just put it 1, rest are basically 0 0 0. So the output which will be generated, it is gonna be 1 1 0. It means is that it is the, you know, binary value of the octal 6. So it is what we call octal to binary converter or encoder basically. The design, how it is designed basically, girls, it's very simple. You check here the inputs. So here are, these are the inputs. Yani Y2 either high here, is it high here, and this one is a high here, and this is here. So 4 places it is high. Okay. And girls, are these min terms, which is min 1 1 1 1 1? See, actually, these are not the min terms here. Why? The reason why I'm saying no like that. See, how many inputs are there? Means I'm 8. So 8 inputs. And do you know the rules? 8 inputs will be generating 2's power 8 combinations, which should be 256, correct? Do we representing here 256 combinations?
No.
So it means is that the inputs are not in the order 0 to 255. So basically these ones are not, you know, representing the min terms of, in terms of inputs. Getting my point? Getting the point? If we represent the, you know, all min here combinations, so this should be 1, second 2, you know, 0 1 2 3, the 256, then we will be saying, okay, this is 1, yani one min term will be like in terms of this one. It is not there. So what is there? It means it's saying that Y2 will be 1 if Y4 input is present. Y2 will also be 1 if the Y5 input is present. Y2 will also be 1 if I6 is also present. So, and this one, so on. So we can simply write this one that Y2 will be high if I7 is high, or I6 is high, or I5 is high, or I4 is high. Do you get this point?
Yes.
Okay, this is here what we are saying. Similarly, you can check for Y1. Y1 will be high if you can see this one, yani I2 is high, I3 is high, like that. Okay, and you can find it. So this way, in terms of inputs, we can see here this logic is OR logic. We can have simply 3 OR gates and we connect these inputs accordingly. So the design of encoder is very simple like that one. So 3 OR gates you connecting according to the these expressions. So this is the design of the encoder. Okay, which is 8 to 3 line decoder. Similarly, we can also design other encoders. Previous discussion. Next thing, girls, in continuation of this combination circuit comes the multiplexer. And what is a multiplexer, girls? Multiplexer is a combinational device circuit, you can say, which is used to select, basically which is used to connect, you can say like that, one of the input to the output source. Yani it has multiple sources, multiple inputs, you can say. Okay, and what else it has? Just a minute, I'll just select multiple sources as a input, and how many outputs are there? Single. And how it is going to be connect, there is a selector. Let's consider an example. We have a music system or sound system which we want to connect to any one of the inputs. So the inputs is, again, there is a rule how many inputs could be there. This is always in power of 2. So like it should be power of 0, power of 1, power of 2, power of 3, like that, like 2's power 2. If I say 2's power 2, it means it is basically 4 input. So we call 4 cross 1 mux, or in what we call multiplexer, MUX. So 4 inputs are there. They are connected to the 4 inputs of this multiplexer, and only one output. But see which of the input out of 4 going to be connected with the Y. It will be selected from the selector, which is here, selector. And what is a selector? If inputs are 4, here what is this value? Because the general configuration is that 2's power n cross 1. This is the configuration for the multiplexer. And here n represent the selection line. So according to the selection line, what I just explained to you, because I said 2's power 2. So how many selection lines will be there?
4.
Selection line.
Input
2. Input will be 4, which are
Yes.
here, you see, but selection line will be 2. So if there are 2 selections line, which is here, so their combinations will be 0, 0, 0, 1, 1, 0, 1, 1. Getting my point?
Yes.
Okay. So if the input is 0, 0, if the selection line is 0, 0, so in D0 is gonna be connected with this output. Clear? Similarly, if the selection line is 0, 1, so whatever is connected to the 0, 1 input, which is D1, it is going to be connected with that one at a time, it's like that. So similarly, you can have another example. If the selection line value is 1, 1, 1, 1, so whatever connected at D3, it is going to be connected with the output. Are you getting this one? Multiplexer now.
Yes.
It is what basically, it is working as a switch. It is working as a switch, yani connecting one input to the output according to the selection line. So selection line is playing a very important role. Yani if 0, 0, MP3's player is connected, which is connected to D0. Then 1, 1, laptop is connected. If 1, 0, this is connected, this one like that. Okay, do you know the remote control of your TV? Okay, and from the satellite, there are a lot of channels are coming. A lot of transmissions are there, but at a time only one radio channel you can watch. So you use the remote basically as a selector, and you choose a particular channel, it will be working. One of the example is the FM radio in your car. In your car you have the radio, right? So at a time there are many radio stations are broadcasting the signal, but are you listening all the radio stations same time?
No.
Only one. And how you choose that one? There is a selector there, a tuner there. You just rotate that one and you can select one of them. Am I right?
Yes.
So this is the way how the multiplexer works. So there is a multiplexer which is used to choose one out of many. So let's see in more detail about this multiplexer. So like one of the example could be like that. We have a single road where multiple lines can be passed. So this is what we have. This is the rotating bridge, you can say. So according to the selection line, according to the priority, okay, this one can go. What about the other at that time? They will be stop. Only this, this car will pass. So according to this, because this has the priority for this one, so it will pass. Okay, next, if the priority is given to next one will pass. So this is basically the multiplexer. Okay, this is a multiplexer example. Now come to the diagram, a block diagram of the multiplexer. As I said, inputs are always in power of 2. So 4 inputs means there will be 2 selection line and 1 output. Is this clear to all of you up to now?
Yes.
Okay. So what are the inputs? Inputs are representing now I0 to I3 and the output is Y. So as I said, girls, if for example, I say the value of selection line is 0, 0, can you tell me which of the input is going to be connect with the output? I0, I1, I2, I3?
I0.
I0. So I0 will be connected, right? So this is the way. So Y will be I0, which is mentioned here I0. Why I'm not writing as a 1 and 0? Because of I don't know. It is just a connection. Whether I0 we are transferring 0 or we are transferring 1. We don't know. We are just saying the connection. So because of switch, it works as a switch. When S1 and S0 both are 0, 0, the Y will be I0. Then if it is 0, 1, Y value will be I1. Yani it will be connected. 1, 0, I2. 1, 1, I3. So truth table, truth table clear to all of you?
Yes.
Okay. So after this truth table, let's see the design. How can we design it? It's very simple again. Y is equal to I0. So I0 is there if S1 value and S2 value is both are 0, 0. And so this way we can design the circuit. So see the design now. First, better to look for 2 to 1 mux. 2 to 1 mux means 2 inputs, 1 selection line. So if S is 0, Y will be I0. If S is 1, Y will be I1. So see the connection. Here we need 2 AND gates, 1 OR gates only because output is only 1. So it is connected to I0, it is connected to I1. When I say S0, so this AND gate, 1 input is 0 and this is 1. So 1 multiplied by I0, I will be getting I0 here. Are you getting this point? And here we'll be getting 0. So what I will be getting here as output?
I0.
I0, because if adding I0 with the 0, you will be getting like that. So this is the design of the multiplexer, which is 2 to 1 mux. Clear? Same way we can check another one. Now just make it a little bit larger configuration, which is 4 to 1 mux. If 4 to 1 mux, yani 4 inputs, 2 selections lines and 1 output. So how it is again generating? We know that yes, here are 4 AND gates corresponding to the 4 input here generating. So inputs either it could be S1 S0 complement, yani 1 minterm it is generating, S1 complement S0, it could be S1 S0 complement, and it could be S1 S0. So 4 minterms are there. So you are just connecting accordingly. I0, what you need to connect with the I0? You see this one, how it is connected? This is coming after the bubble. Yani this is S1 complement, other one also S0 complement, and then you connecting this way. Similarly, this is I1. So how you write the minterm 1? You will be writing S0 complement and S1 complement S0. You look here. We will be connecting the same way. S1 with the complement. See, S1 with the complement connected here. And S1 is connected directly. Can you check it now? Clear?
Yes.
Okay. So this way we can design the multiplexer. Basically, the inputs for these AND gates are 1 input like that, and another 2 inputs will be the minterms generating by the selection lines. This is the design of the multiplexer. Now, guys, one of the other application of the multiplexer is that quad 2 to 1 mux. Quad yani, what is the meaning of quad? 4.
4.
Correct? 4. So here, girls, we are using 2-to-1 multiplexer, but how many we are using? 4. Okay, and so 2-to-1, if we have 2-to-1 multiplexer, so how many selections lines will be there? 2-to-1 mux.
4.
Selection line.
Only
Selection line rule, I told you, the selection line rule is 2's power n. So n is the selection line, and this calculation is the input basically. These are the inputs, and S is the n is the selection line. This is the rule. So how you write 2-to-1? 2-0. So it means 2 input. Sorry, 2 input and 1.
and one output. One selection line. Sorry.
And output will always be 1 for the
Always.
yeah, always be 1. So like what we are having, we have this 1 mux, 1 mux, 1 mux, 1 mux. That's why we are saying quad multiplexer. Now, so for example, girls, we have two users, user X, user Y. Both want to transfer 4 bit at a time in parallel. So for example, the bit is X3, X2, X1, X0. Another one is Y3, Y2, Y1, Y0. Okay, so 2 transmitter. Okay, they wanna use the transmission media which is available here to transfer their information parallelly, all bit together. So how can we make it? We just make this selection line common, so that when I say S is equal to 0, it means is that I naught is gonna be connected with the Y. Are you getting this point? See this? So what I will be getting as output? Will I be getting X3, X2, X1 and X0 as an output here? Clear?
Yes.
Yes.
Okay, means we have given chance to the X user to transfer its information 4-bit parallel. Clear?
Yes.
Yes.
I want to give another user chance. So what should be the value of selection line? 1.
1.
When I say 1, it means is that I1 is gonna be connected now. Clear? And
Yeah.
Y's output will be there. Yani Y3, Y2, Y1, Y0 will be there. So this time user Y will be transferring its information if the selection line is 1. So this is one of the arrangement utilization of the multiplexer which we have seen. Okay, it is the way. Okay, next the design. Design is very simple. In designing, what we have 4 AND gates for the implementation of the X, or we can say A here, and 4 for the B. What this is for the Y. And see here the value of S. As I told you, if S is 0, so X was working. So that's why if X is 0 here, girls, for example, so the output of the inverter will be 1. And see, it is connected here. So one of the input of these AND gate is 1. Another one is the enable control, girls, which could be there. And we know that it should always be 1 if it is working. Okay. So it means is that this is representing the in E, which is also 1. So now what is controlling the output of these AND gates? We will be getting here A3, A2, A1, A0. And what you will be getting the output of the lower, this one, because you see S is 0 and it is directly connected to all inputs. It means is that one out will be 0. So what you will be getting as a here A3, A2, A1, A0. Yani user A is transferring the information. If S is equal to 0, if S is equal to 1, user B will be transferring the information. This is the way. Is this clear to all?
Yes.
Okay.
Yes.
So the block diagram will be very simple. This is the block diagram. So this is user A, 4 input, user B, 4 input, 4 outputs this time, because these 4 gonna be connected either this way or it is going to connect another way this way. Depend upon the selection line. Enable should be 1 always in order to work it. If enable is 0, this will not work. All the output will always be 0. You know that rule. Is this clear now?
Yes.
So this is the another way to use the multiplexer basically. Okay. Girls, multiplexer will also use to implement the function as we have seen for the decoder. And see how can we do it. See this one, f is equal to, we have this function, provided we should have minterm. So can you draw the truth table for it? You know that 2 inputs, so the combination will be 4 and f will be 0 1 3. Is it clear, this truth table from this function?
Yes, it's clear.
Okay, and how many inputs we have? 2. So we will be using this, yani 2 will tell you the selection lines n value. So like 2's power n, we have the number of inputs for the mux. So these 2 is telling you the number of inputs, yani n value. So 2's power 2, that is 4. You're getting my point? And n 2 will be selection line. So see the design, very simple. What you will do, you will connect x and y. As I said, this x and y is basically going to connect with the selection line. 2 inputs, yani 2 selection lines are there. They are connecting like that. Okay. Now, what about the f values? F values are going to connect with the input. Exactly same. Now you can verify the truth table for any input. You want to check for it? See this one. If I say here 1 and 0 as a selection line, can you tell me which of the input is going to be connected with the output? I2, I1, I2, I3, whatever. Is this going to be connected with that one or not?
I2.
I2, yeah. So what will be the value of f? Because I2 is fixed value now, constant.
0.
0. Is this the verification of the truth table or not? Getting this one?
Yes.
So this design is very simple. You just connect the value f values directly to the input, because earlier we don't know what are the inputs for this one, but now this is constant according to the given function. So this is the one example. Okay, any one application of the multiplexer, we can implement any function. See now this one, girls. So how many inputs are there in the given function? 3. So number of selection lines will be 3. So if selection lines is 3, how many inputs will be there? 8. Output will always be 1. We know that. So we will connect. Then we will draw the truth table first. The first step is to draw the truth table, and then connect the inputs with the selection lines and the outputs with the input of the multiplexer. Is this clear to all? Check this one. So these are f basically, and these are inputs of this given function. So we can implement any function provided you should have the minterms. If you have the minterms, you can design it. Clear, guys? Up to here? Any question?
Clear, doctor.
Clear.
Okay, so I am just stopping because the time is short and I have another lecture which is